This video is on rolling. The cylinders shown start from rest. In case 1, there's no friction. In case 2, there is. In both figures, use variables and other symbols to convey what the cylinder is doing when it's at the dashed location. If there's no friction here, then the object is not rotating, but of course it will be sliding. So I can maybe put a little arrow here and say V. It's going that way. And maybe I want to make a little notation that omega here will be 0. That cylinder will not be rotating if there's no friction. Here, it will be rotating. It's going to be rotating that way. And it will be moving too, obviously, in that direction. So far, so good. Part B, notice the straight line painted on the solid cylinders. Into each dash cylinder, draw an identical line oriented in a way that is plausible or likely based on the physics of the situations. In the case where there's no friction, this painted line here is going to be at the same spot because this cylinder hasn't rotated. I tried to draw that in the same spot, but this painted line will not probably be at that very same point. So, maybe it's pointing like that. You can point it in any direction you want. The point is, it's not right there where it was because this cylinder is rolling, whereas the one on the top is not. Let's do a little conceptual work here before we get into any problems. For rolling objects, in our free body diagram, we must draw each force where it really acts. Not necessarily at the center of mass, which we've always done up until now. Whenever we've done Newton's second law, we've always assumed that all of the forces are acting at the center of mass. You cannot do that when you're dealing with rolling objects. Also, we will choose the axis to be through the object's center of mass. There are a couple ways you could do this, but this is the way that I'm going to show you how to do this. And the reason is because when you do that, there are two forces that will contribute 0 torque. And those will be the normal force and the force of gravity. We're always going to choose the axis to be through the object's center of mass, or typically we will. And the reason that these two forces don't contribute torque is because the lines of action of these two forces go directly through the center of mass. So if you choose the center of mass to be the axis, those two forces won't appear in your equation, and it should make things a little bit simpler for you. Lastly, whenever you're doing rolling problems, you need to use Newton's second law for translation, which we know and love to be F net is equal to mass times acceleration. You also have to use Newton's second law for rotation, which is the net torque is equal to the moment of inertia times the angular acceleration. And finally, you need to use a bridge equation that connects these two. Now, what's the bridge equation that connects these two equations that I've already written? It is that the linear acceleration is equal to r times the angular acceleration. You might remember in a previous video, I gave you the stupid little mnemonic of tra la 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 la, where r is the radius of the object, a stands for the angular quantity, and t stands for the tangential quantity, or translational quantity, either one. Those three equations are all going to be needed in order to solve rolling problems.